Let's talk about groups. We have our giant pile of objects, and I want to group them. So let's think about what we could do. This is particularly useful when we think about those equivalent methods we were talking about with our division principle on Wednesday, but I want to think a little more generally at the moment. Dirichlet, a French mathematician studying probability theory, developed this idea thinking of a drawer of cabinets. So I've got drawers in a bureau, a dresser, right? So let's suppose I have a group of objects. There are k plus one of them. And I'm going to put them in k containers. I have shirts that are going into the drawers of the dresser. I have pigeons going into little cubbies to be pigeonholes. The reason we call this the pigeonhole principle. What can you guarantee me must happen as you load up the shirts into the drawers? Colin? At least one container must have more than one object. At least one drawer contains two shirts. At least one pigeonhole contains two pigeons. I don't know how many drawers, how many containers will hold more than one object, right? But I have to have at least one. There's an immediate corollary, takes me all the way back to chapter 2 here. Suppose I have any function from one finite set to another. If the cardinality of the domain is larger than the cardinality of the codomain, what do I know about this function? If this had k plus one things in it and this had k things in it, what could I get from here? I think about the properties we came up with when we were talking about functions back in chapter 2. I had functions that went from one set to another, drew my little arrows between the objects, right? And then we talked about some of the types of function properties we could have. The two main properties we spent all that time on. One-to-one and onto. What does it mean to be onto? Everything where has an onto.
Set A doesn't match with set B.
Almost.
Everything in set B.
Everything in set B got hit by something in set A. That's what needs to be on to B. Cover all of it. Remember, we use the word on, surjective. What's it mean to be one-to-one? Aha. If there are more things in the domain than there are places for them to go, what has to happen? by the Dirichlet principle. Think about the things in A as your pigeons and the things in B as your pigeonholes. You have more pigeons than holes. What has to happen? I have to have one pigeonhole that gets two pigeons. My function can't be 1 to 1. Okay. How can I apply this? This course is graded on a letter grade scale. When everyone is here, there are 15 students in this course. What does that guarantee mean? Because there are only 12 grades here, and there are 15 of you, at least 2 people will have the same grade in this course. That's all I needed was to count. How many people? How many options? Huh. Okay. Let me go a little crazy here. How many people do you think there are in Westmoreland County? Seems like a crazy number to have, except for your fingers. How many hairs do you think there are in a human head? You have the internet. Time to do some Googling. I need 2 numbers.
Westmoreland County is 352,000 to 353.
So I'm going to go with approximately 350,000.
$90,001.
So we'll use the big end, 150,000. A full, lush head of hair. Not what I have. I guarantee you there are 2 people, at least, in Westmoreland County that have exactly the same number of hairs on their head. Imagine the pigeonholes as the numbers from 0 to 150,000. I've got 350,000 people. You find the number of hairs on your head. stand in that line. There are more people than there are places for lines. There have to be at least two people standing in the same line. That's a claim I never would have been able to think about until I think about the way the pigeonhole principle operates. There are at least two people with exactly the same number of hairs on their head. There are at least two books in the Library of Congress with exactly the same number of words. Same idea. I'm sure the number of words in a book averages somewhere around 500,000. Big, heavy novels, the Game of Thrones series, 1,000,000 words. There are way more than 1,000,000 books in the Library of Congress. Things we think of as separate, uncountably wide, huge numbers, they overlap quite a bit in ways we don't think of. I can go a step further. Just thinking about this example, I can go a step further. Not just that there are at least two, there have to be at least three. How can I guarantee there's at least a third person? Let's think smaller numbers for a minute. I want to take this idea and I want to generalize it. Instead of just thinking of k plus 1 objects, let's think of n objects in k containers. And I'm going to make my numbers smaller this time. So let's think of 10 objects and 4 containers for an example. If I have 10 objects and 4 containers, why can I be sure that at least one container has 3 things in it, not just 2? Right?
Because those two would only be 8.
So 10 divided by 4 is 2.5, right? So I put 1, 2, 3, 4, 1, 2, 3, 4. That's 2 in each. I still have 2 more things to go. I have to take that fraction and round up. And there's my round up thing, the ceiling operation. Take n divided by k and round up. Now go back to Westmoreland County and hairs on the head. How many people in Westmoreland County? How many hairs on the head? 350 over 150 is 2.3. I got to round up to 3 people. Now, it might be that it is a very, very lopsided behavior. And instead, I could think of those 10 objects in the 4 drawers. I could put all 10 of them in the first drawer and just leave the rest empty. My distribution doesn't have to be equal. But I guarantee you at least one of the drawers has to have n over k rounded up. Because what do I do with the fraction? I have a group of 100 people. How many of them must share birth month? Evan? 9. 100 divided by 12 is 8 point something. It's got to be 9. Birth date, date of the month. Because there are 31 days in a month at most, 31 options to choose from. 100 divided by 31 is 3 point something. It's got to round up to 4. Now I can actually use this the other way around. In a standard deck of cards, there are 4 suits. Hearts, spades, clubs, diamonds. I want you to guarantee me 2 cards in the same suit. How many do I need? 3 cards in the same suit. How many cards do I need? I want to know how many objects I need. I know the number of containers, and I know the number of things I want to match my container. So really, if I say that the number of cards is n, and I have 4 containers, the suits, then what I want is n over 4 equals 3. But that's rounded up, right? So really, I just have to have the fraction n over 4 itself to be bigger than 2. It just could be anything, even just the slightest bit bigger than 2, and that would be enough. Oh, well then n has to be strictly bigger than 8, which means I need 9 cards. And this is another case of worst case analysis. Remember when we talk about algorithms? We're trying to figure out how we would analyze how many steps it took. We looked at the worst possible thing that could happen. I deal a cards to you. When can you guarantee me you've got 3 of the same suit? Well, it could go heart, spade, club, diamond, heart, spade, club, diamond. That's 8 cards, and I still don't have 3 of the same suit. But as soon as I deal card number 9, one of those drawers has a third element. Same principle. What if I said specifically I want 3 clubs? At that point, the pigeonhole principle is not the right thing to think about. But my worst case analysis is. So now think of dealing cards. What's the worst thing that could happen to you if you're looking for clubs? I got to pull all the other suits before I get the clubs. That's 13 hearts and 13 diamonds and 13 spades, then 3 clubs. That's a lot more cards, isn't it? That's 42 cards. A lot more than 9. Let me go back to phone numbers for a second. When we were talking about phone numbers, ignoring area code for the minute, there was the exchange and the extension. And the later version of the Telecom Act said that I only need to not have a 0 or a 1 here. But everything else could be anything else we wanted. How many phone numbers are available in 7-digit form? Well, careful. How many options are here? But then here, so it's 8 times 10 to the 6th. I thought you said 9. That's why I was confused. So that's 8 times 10 to the 6th, or 8 million. There are 13 million people in the state of Pennsylvania. How many area codes do we need? 2. Yet, as of 2018, we had 10. As of today, we have 15. There are 15 area codes. We only need 2. But there are 15 of them. So sometimes it's not about efficiency. Sometimes it's about the way in which we disperse these things. Because remember, we sold phone numbers by the exchange, not by extension. So it was a very different setup. All right. Questions so far? The reason I like pigeonhole principle is because it lets me think about proofs as counting arguments. Can I count these two things in two different ways to somehow show that I must have them be equivalent? Or can I show that there must be some commonality in my group? This sounds like an absolutely psychotic statement on its face. Among any collection of n plus 1 positive numbers, positive integers, all less than or equal to 2n, there exists at least one number that divides some other number in the list. I don't care what value of n you pick. Somebody give me an n.
5.
Okay, that means my numbers go from 1 to 10. And you have to pick 6 of them. I don't care which 6 numbers from 1 to 10 you pick. At least one of them has to divide another one. Sure. Why? This sounds like a load of bullshit. First of all, if I pick the number 1, 1 divides everything, right? On the other hand, if I don't pick the number 1, I got to do something different with my other numbers, right? How would I prove this idea? I would like to somehow, instead of looking at 2n different choices, I'd like to look at n different choices. Why do I want to get to n different choices? I've got n plus 1 numbers. If I can figure out how to put them in n boxes, pigeonhole principle will probably apply. So now I figure out what the boxes look like. One divides everything. So I'm not going to pick 1. But that means I probably should pick 2. If I pick 2, what can't I pick? Because 2 will divide even numbers, right? So maybe I need to count numbers by how many 2's they have, right? So I think of 2, and that leaves out 4 and 6 and 8 and 10. But 3 will work, 5 will work, 7 will work. But what happens if I pick 9? It's divisible by 3, isn't it? Oh, wait, okay. Hang on a second. Let my numbers A1, A2, up to AN plus 1. Those are my numbers, the ones I picked. And what I'm going to do is I'm going to take each and every one of these and write them as some power of 2 times an odd number. AJ is equal to 2 to the sum power times Qj, where Qj is odd. So that's why I said I could use 3 and 5 and 7, right? Because 3 and 5 and 7, they were odds already. I just really took out the factors of 2. But if I'd picked 6, I'd write 6 as 2 times 3. If I pick 8, I'll write 8 as 2 to the third times 1. So this must be odd. What's more, I know these numbers, AJ, are all less than or equal to 2n. Well, that means that Qj is less than or equal to 2n, and Qj is odd. The following is a stupid sounding question. How many odd numbers less than n are there? How many odd numbers less than 10? Oh. How many odd numbers less than 30? How many odd numbers less than 2n?
2.
Less than 2n is n, right? Oh, qi 2n. There are n possible values of Qj. I just found my boxes. I just found my boxes. I want you to line up the A's by which Q they contain. So, for some value of Q, we have QL equals QM with L comma M between 1 and n plus 1. At least 2 of my numbers have to have the same odd part. Right? Because there are only n choices of odd parts, and there were n plus 1 numbers. There's my pigeonhole principle. All right. So, in what? So what? What does this matter? I've got 2 numbers that have the same odd part. And each of those numbers is written like this, right? So it's some power of 2 times the same thing. So AL is 2 to the KL times Q, and AM is 2 to the KM times Q, where this value is our value Q, the one that they had in common. Unless those 2 numbers are exactly the same, one of those powers must be smaller than the other. I don't know which one is smaller, but one of them is a smaller power. Otherwise, I pick the same number twice, and every number divides itself, so I would be done right there. Which one do you want to make the smaller one? Without loss of generality, we can assume which one is smaller, L or M.
L.
Without loss of generality, assume KL is less than or equal to KM. Then AL divides AM, since AM is 2 to the KM minus KL times 2 to the KL Q. which is some number of 2's times AL. So AL must divide into AM. Ta-da! Now, Jolanda, when I got to 9, you're like, wait a minute, we already chose 3, right? They have the same odd part. The 2 to the 0 times 3 and 2 to the 0 times 9, they match. Even if I'd left out 9 and tried to choose 6, they both have 3's in them. So I can do this by odd part. But the reason is I had to choose n plus 1 numbers less than or equal to 2n. I had to have one more pigeon. I had pigeonholes. There are a large number of mathematics ideas that deal with large collections of things. Let's go to a party. I want to have a party. The minimum number of people at a party is such that there are either this many people who are friends, all with each other, or this many people who are all enemies with each other. It is possible to guarantee that in a group of 6, you will have at least 3 who like each other, or at least 3 who hate each other. But finding the exact values when n and n are larger than 3 is really difficult. Ramsey numbers give birth to an entire idea. The exact values of only 9 Ramsey numbers are known. We know R44 equals 18. But we only know for R55 that it's somewhere between 43 and 48. And we can't prove which value it is. Now, I don't care about a party. I don't care about friends and enemies. Let's turn this into a networking problem for a set of computers. I have a pile of computers. I need to make sure that at least this many of them can communicate with each other on the same protocol, or are locked out from each other on the same protocol. These 5 are secure. These 5 are interdependent. That would be the Ramsey number R55. How many computers do I need? If I have a group of this many computers, how many different types of clicks can I get where they're all mutually connected to each other or all avoiding each other? This is a graph theory problem. This is my plug for next semester's graph theory course, people. Take graph theory. There are all sorts of applications in computer networking, in people networking. Not just parties. A very famous mathematician whose work was in number theory is a guy by the name of Paul Erdős. Hungarian mathematician. Paul Erdős was really very famous. They wrote a book and made a movie both about him. The book is titled The Man Who Loved Only Numbers. Erdős was a little touchy. Erdos would occasionally simply show up at somebody's door, another mathematician, say, I came to work with you, I'm here for the week. No warning. Expecting you to put him up, the whole 9 days. That was a little weird. And they would have a conference suddenly in this guy's house. And 30 people would show up and they'd all do math for a week. Erdos would throw problems out. I think this is deep. And he'd be right. But I don't know how to prove it. Maybe you can help. And the people would work together at this conference. Somebody made a graph. We defined the distance to Erdos, like the 6 degrees of Kevin Bacon routine. How many people have you worked with who's worked with someone who's worked? How far are you from Paul Erdos? By the way, unfortunately, my Erdos number, my distance is infinity. Because I have no co-authored papers with anyone who's ever authored a paper with Paul Erdos. I only have a total of 3 authored papers at all. All three of which I'm primary author, and the other people were working with me. They were students here. So I'm kind of screwed. Dr. McNabb, on the other hand, last week published a paper with her advisor, which makes her Erdos number 3. It's 3 people, from Leah McNabb to her advisor, to one of their co-authors, to Paul Erdos. This got so well known as an idea that somebody actually physically drew the graph of all the connections of all the people who've ever worked with Paul Erdos, and then all the people who worked with them. The actual graph is available online. You want to talk about connections between things? You talk about connections between people, between objects. That's what graph theory is about. And the pigeonhole principle, a really good way to approach it from a very small set of numbers. So I hope to see you next semester in graph theory. But that's all I have on the pigeonhole principle. We'll talk more about counting stuff on Monday. I will see you all then. Have a wonderful weekend. Write it down. We're early. That never happens.